Okay, I propose we start. Good evening, everyone, and welcome on this beautiful Wednesday evening. Happy that you are with us tonight. Our presenter is Michael Sluydts. He is a researcher at UGent and is also founder of his own company, Hypothetical, that is occupied with deep learning consultancy. And he will be talking tonight about AI, artificial intelligence, and the search for new materials. So without further ado, Michael, I'll give the floor to you. Your screen is already shared, I see.
Yeah, thank you, Fleur, both for the introduction and the opportunity to talk here tonight. So as Fleur already said, I both do research and consultancy, and this represents a bit the two halves of the presentation that we will be looking at. So we have physics, where at the university we use quantum mechanical simulations to really get accurate predictions for properties of materials. While with AI, we more focus on getting these kind of pragmatic models, which really get insights from data without necessarily having a kind of rigorous mathematical background. And today I'll try to show you how you can combine these two to get a nice combination of getting fast new materials. All right, so let us get started. So first of all, let us think a bit about what materials actually are. So if you think about materials, you'll quickly reach the classics. So wood, concrete, steel, things that do not really spark your imagination, but which are all around us. Now, despite this, a lot of research actually goes into developing these materials. A few hundred years ago, we would not be able to build skyscrapers. Nor any kind of electronics that you have before you. So it's very important to not forget just what effort goes in there. Now, a good question is, how do we actually discover all these materials? I mean, wood is easy, but if you think, for instance, about the silicon technology, which goes into your phone, then you actually have to start from white sand and somehow get this lifeless sand into the living thing that is your electronics. And to kind of explain to you how we got from sand to this modern technology, I'm going to tell you a story about the origin of material science, which in the end is the physics of materials. And like many good stories, it starts very long ago. More specifically, as far back as we can go, being the dawn of time. So at the dawn of time, we had, of course, the Big Bang. Now, at the Big Bang, that was not really a good time for material scientists. And there are two main reasons for this. Any material scientists that might have existed at that time would have come into existence out of pure randomness due to the high energy available at that time. But their existence would have been very short and very unpleasant. Now, there is a very important second reason why it was not a very good time for material scientists, and that is, of course, that if they were conscious, they would have observed many interesting particles that we physicists actually dream about seeing nowadays, but what they would not have seen is actual materials, since materials formed much later in the evolution of the universe. The universe had to expand first, cool down, and form atoms, which then formed stars, which got polluted and then eventually exploded, spreading out heavier atoms, which then coalesced into the planets and materials that we have now. And so it is only much later that we actually get to materials and, of course, to material scientists. Now, so let's fast forward a bit to the time of the first material scientist. And this image is, of course, iconic in the history of science. You all have imagined this moment, and it is, of course, the invention of fire by the great scientist Grog. Grog here, of course, through the invention of fire, did not actually look at any materials. Fire is just kind of a plasma. And so what's important here to realize is that the main invention that we should be looking at might more be the materials that led to the fire. And thus we look at Josephine here, who invented the two rocks which you hit together to create the sparks which led to this fire. And now I will go through the history of Josephine. So Josephine started her career much earlier. She was a berry picker, which she started at age 5. And as she went onto her first berry picking journey, she stumbled upon a rock. And as she did this, she made an epiphany. She realized that this rock is hard and might actually be useful for many kinds of applications. More specifically, you can use this rock as kind of an axe. Now, of course, while her original job as a berry picker was very nice, she had tasty and organic berries, this new epiphany led her to a much more interesting path. So with the invention of stone, we entered the Stone Age. And this was also the first materials property that was invented, namely hardness. If you realize that stone has this kind of property, you can actually make comparisons of stone. You can create a ranking. So if you hit two stones together, one will be harder than the other might chip, the other one might be more brittle, and things like that. And if you think like this, you're already kind of creating a material space. So you can imagine there might be like this space of rocks, and on one side of the space, you will have soft rocks, on the other, you might have hard ones. And somewhere in there is the optimal rock that you might want to find for your application. Now, this is not the last invention that she made. The second one here is the combination of materials. Namely, while rocks are very interesting, there are many more interesting materials that have very differing properties. And you can imagine this like being a kind of a separate part of this material space. While rocks vary strongly in hardness, still most rocks are going to be harder than this wood. The wood is also much easier to shape, let's say, and it is much warmer to hold. And so there are very distinct applications for rocks and wood. And it is very important to realize that all the woods, let's say, are much closer together in this material space than the woods and the rocks are. All right, let us proceed. So since then, material science has gone through many evolutions. We went to the Copper Age, where we actually learned that if we heat up materials, the copper can be extracted from certain rocks. This was likely also an accidental discovery. It was a bit later then that we applied this to many other materials, finding metals like tin and lead and so on. And as we mixed these materials, we invented bronze. Then still later, we got to the Iron Age. And this already starts making things more difficult, since to create iron, you need to obtain very high temperatures. And this requires the development of special equipment. And so the realization we must make here is that as you want to develop more complex materials, processing also becomes very important. So this is very different than the start of our story of Josephine, where we could just walk around in nature and find a material. Here, we really have to first find a material, but it only becomes useful after we send it through a series of processing steps. And this makes it very difficult to immediately recognize what might be an interesting material. And this is one of the reasons why up until this day, certain materials remain very difficult to reproduce. One example of this is shown here. So this is Damask Steel. Nowadays, we kind of think that we have discovered how to make this, but the reason why it's so special is actually because it contains carbon nanotubes. So these are very small tubes made out of carbon that nowadays we find very interesting as kind of nanotechnology. But somehow these, let's say, primitive scientists were able to discover this kind of application without all our modern technology. And one reason why they were able to do this is because they spent their entire lives trying to improve the properties of this specific material, but also because they had very limited tools available and very limited options available to them. And this might seem counterintuitive. But if you have a lot of options available, you can reach, let's say, better properties if you try to optimize something, but there's a very high chance you might get lost in your options, in your knowledge. You will try lots of different things, and this makes it much less likely that you will find the true optimal solution given all your possibilities. So in a sense, if you combine luck with skill and limited let's say, or strong constraints on what you can do, you might actually find more interesting things than if you have a lot of options available. All right, so this brings us to the current age with an additional problem, and that is that we are very greedy. So nowadays we want more exotic materials like superconductors, which do not lose any heat loss, for instance, as we send electricity through superconducting wires. We want thermoelectrics that convert heat back into electricity, and things like transparent conducting oxides. So basically metals that are fully transparent, for instance, to have a screen that does not crack. In all these cases, it is even more difficult to recognize what material might be suitable for these kind of applications. If you hit your toe against a superconductor, you will also curse and likely throw the rock away, but you will likely never know that it was a superconductor. So we can ask ourselves, where do we find these kinds of materials? And for this, we will rely on our knowledge of the modern age, namely that we are in the atomic age, where we realize that all materials are made out of atoms. So in this age, this age started when we discovered chemistry. So it is actually very surprising that chemistry works at all. So we started using it more at the start of the 20th century in its current form. And somehow, by making these approximations where we write down equations on papers and write down these kind of 2D structures, we are able to model very complex chemical processes. While in reality, these molecules look a bit more like this. So they are 3D structures with a 3D geometry, and they are actually still moving around a bit under influence of temperature. So it is kind of special that by making these simple approximations, we can actually do chemistry. So what can we learn from this? First, that chemists' rules of thumbs actually have quite a lot of value, and that physicists who really look at everything through equations should sometimes be a bit careful when overcomplicating things, while at the same time these rules of thumb that chemists use might sometimes be a bit too simple, and that they should be a bit skeptical of the kind of applications that they use this for. All right. But with this knowledge, we can actually study how materials are formed, and we can kind of design them. Now, with quantum physics, we can actually get very exact material properties. This comes through Schrödinger's equation, which effectively tries to solve this psi here, which is the wave function. And the wave function contains all information about the material, and you can extract all properties from it, but it is very difficult to obtain. One other thing we can get from this is an energy. And the energy is also it's something that feels very natural to us because we use it in our language, but we need to be a bit careful about what it actually means. So the purpose of this energy here is kind of to compare what is most stable, meaning if you have a material, it could occur in many different types of crystals, many different types of configurations, let's say. And it is by comparing the energy of different types of orderings of our atoms that we can see which ones are really most stable and which will occur in reality. And thus, we can actually solve Schrödinger's equation to extract all our properties. Now, the problem is that solving this equation is very difficult. Before continuing with this, let's have a look at this figure here. So, as I mentioned before, materials actually come in crystals, and crystals are actually very ordered shapes of atoms. Not all materials are crystalline, but the ones that are have very specific properties that we can easily simulate. And so you can imagine a crystal as this kind of an ordered lattice, and a box which has been filled with atoms, which we typically represent as these balls here. But you can, in theory, arrange your atoms any way you like, but only the ones that have the lowest energy will actually occur in reality. Okay, so if we have this kind of geometry that we ourselves create and we give it to a computer and tell it to solve Schrödinger's equation for this, we can actually do this given some approximations and get the material's properties for this material. See if it's, for instance, stable or not, or a good conductor or not, for instance. But we need a lot of compute power for this, so we can only do this for a limited number of materials. This, for instance, is one of the biggest usages of the supercomputers here in Belgium. All right. And this is actually the type of research that we really do at the Center for Molecular Modeling. We take these kind of nanoscale structures. Here, for instance, you see a kind of porous material through which various gas molecules are sent. For instance, to filter gases or to help chemical reactions occur in this gas by the molecules sticking to the sides of this sponge, let's say. What you see at the bottom here is a more classical material. It doesn't have holes, it's just a box that is filled with atoms. And this box you can imagine being extended in all directions to build the materials that you are used to. For instance, if you have a metal desk, if you zoom in enough, it will look a bit like this. All right. And then, of course, the challenge is to use these insights from the very small to go through these macroscopic materials that we have in the real world. All right. So now you know that we can use quantum physics to determine the properties of materials. So now let's start thinking a bit of how this chemical space, this material space that I mentioned before is structured. Now you can imagine that there is this space of all possible materials, and with all possible materials we really mean all materials. Like if you take, you know, all the atoms in the universe and you push them all together to make a giant chair or something, that is all materials. Most of these are completely nonsensical, and we are only interested in the materials which are actually stable, which is a very small amount. Now among the stable materials there are of course many applications. So you can imagine, like we said before, that there is a small space where rocks live that are softer and harder, and that this kind of there are many different rocks which span the range of all possible hardnesses. But for other properties, it might not be that simple. Maybe superconduction requires very specific tricks kind of to occur in the material, very specific conditions. And this may mean that there are only very small spots in this space of all stable materials which exhibit superconductivity, and that they may not all be related to each other. For instance, this might be these yellow spots here. So the trick is a bit of finding the needle in the haystack, that is this stable materials here. So let's examine a bit how we might do this. Now, before we can do this, we can ask ourselves the question, are there still materials left to discover? Because that in itself is already not that self-evident. We have already discovered around 100,000 materials, and it is not, it does not mean that there will be infinite new materials. So let's think a bit about that first of all. How are we going to do this? We're going to see if we can create a Drake equation for materials. What is the Drake equation? It is an equation that the scientist Drake, not the rapper or the pirate, imagined long ago. And it's meant to estimate how many intelligent species there might be in the universe. And how do you do this? You imagine how many galaxies there are, how many solar systems in each galaxy, how many planets in each solar system, and then how many of these planets might actually be suitable to life. So by estimating all these different factors, you can estimate how many species there might be. And we will do the same for material space, where we have different types of materials, different families. Within those families, we have the individual materials that may be stable or not, and only then some of these stable materials will be suitable for specific applications. So let's start with this. All right, so if we want to build materials, we of course have to start with elements that we find in the periodic table. So to remind you all, the useful part of the periodic table somewhat ends here. So we will look at the first 86 elements, of which the last 3 are already somewhat radioactive and unstable. So polonium is only interesting for Russian spies and people who want to do a PhD with us on a very interesting nuclear reactor, which I will get back to later. But yeah, the main interesting materials are usually built up to like bismuth, let's say. And of course, within the periodic table, we have the columns, which show very similar chemical behavior. And then as you go down in the columns, effectively the atoms get bigger. But you can kind of see this also as a continuous space where elements which are nearby in the periodic table kind of behave similarly. So let's count a bit how many materials we might be able to build with this. Each of these materials will exist in a stable crystal structure. Even elements like oxygen, which we are used to being in a gaseous form, will eventually form a kind of ordered crystal if you cool them down enough. So let us count. If you look at materials with one element, there will be 86, one for each element. If we then make combinations of 2 out of these 86 elements, then we have 86 choices for the first element and 85 for the second, leading to 7,000 total combinations. If we then go to 3, we already have 300,000 combinations, and it keeps going like this. So if we put this on a graph, you see here that the most elements or the most materials should be made out of 43 elements, and that there should be around 10 to the 25th materials of this kind. If we then add up all elements, we see that pretty much all materials in the universe should be made up out of 43 elements. Now, I've never seen a material with 43 elements, which means that we are probably making some kind of reasoning mistake here. And the reasoning mistake is the following. If we want to make a material which contains many elements, we have to combine it kind of from simpler materials. What does this mean? So imagine we are making a binary material of 2 elements, then we first have to kind of like take a scoop of each of these elements, which means we have to break the bonds of this stable crystal for this single element, and then we have to form new bonds between those 2 elements. And it is not guaranteed that the new bonds that we form between these 2 elements are more stable or lower in energy than the bonds you might form in the individual crystals that you might have for the individual elements. And thus, it might just fall apart again, even if we put a lot of effort in trying to make this binary crystal. And thus we have 2 options, either it sticks together or it does not. And this of course continues if we go to 3 elements, but now we have many more options. The 3 elements could stay separate, or we could form any of these 3 binaries, or we could form this kind of ternary material. And in fact, so the ternary material could fall apart in any kind of combination of the materials that you see here. So this means that all the bonds that are in this ternary material need to be better than any kind of bond you might make in all these other 6 materials. And as you go to 4 elements, 5 elements, and so on, this gets more complicated. All right, so you can actually count the kind of ways that these materials might fall apart, and these are the Bell numbers. And these are plotted here on the red curve. So you see that these Bell numbers actually skyrocket even faster than the actual number of materials you might be able to create. And if you look at the one material we can form with all 86 elements, if we pretend they all have the same geometry, then there are 10 to the 100th ways that this one material might fall apart. And thus we can imagine that this is pretty much impossible. So somewhere along this line, there will be a limit at which point it will become very rare to impossible that we can create a material that is so complex, just because it has so many ways of falling apart. Now, where this limit is actually not yet known. So you can look a bit at the databases we have on existing materials. So this is a figure of a few years ago. At the top here, you see the number of materials that are reported. And at the bottom, you see the same thing, but ones that are actually stable. So at the top here, there are also materials that were created under very high pressures, under some specific temperatures, that were grown on top of other materials. And in all these cases, that fall apart as soon as you remove them from these conditions. So if you look at actual stable materials, then you see that binary and ternary materials are discovered at about 500 per year. And quaternary are already like 300 or something, and we're actually going down here. So the question is a bit, is that because we are, bumping into this effect we saw on the last slide, that the materials are becoming too complex? Or is it just that, we as humans are lazy and are just trying to discover all these binary materials before we go on to the quaternaries and so on? So we decided to investigate this a few years ago, and we discovered actually we discovered an interesting family of materials, namely quaternary interfaces, which effectively combine these kind of alkali metals. So these are the kind of things that explode loudly if you throw them in water, and they get combined with kind of molecules created in this part of the periodic table with elements that we know well, such as silicon and sulfur. And with this, we decided to kind of investigate how many of materials there might still be possible to make in this subfamily of material space. So what we first did was try and make a map of this. This is already kind of an application of artificial intelligence, since, as you can imagine, it is very difficult to put materials in a map. So what you do is you kind of make a description of each atom that is in the material. So we use the kind of properties they have as a kind of way of describing these atoms. And then we use an algorithm that looks in this space of all these materials and kind of tries to fit a 2D surface through all the points that are in this space and pull it flat. And that's what you get here. We also applied a clustering algorithm, and what these clustering algorithms do is try to group similar materials together, which are the colored spaces here. And these colored regions can actually be seen as material families, of which a few materials exist. The red dots are all materials which have a very unique crystal structure, and no other material has been found yet that has the same crystal structure, which is about 60%, I think, or 40% of this map. So this is also very interesting. Does it mean that they are truly unique, or just that we haven't explored enough yet? And so what we decided to do was take 3 of the material families within this space and try to estimate how many materials there are still to be found to put in our Drake equation. So let's first have a look at our Drake equation. So like I say here, estimate the number of materials based on these observed materials is a bit like estimate the number of planets based on what we've observed of our galaxy, the Milky Way. So if you would write down a Drake equation, it would look a bit like this. So the number of planets with life is first kind of a scaling factor. So we divide the number of planets in the total universe by the number of planets in our galaxy. So how many galaxies do there fit in our universe? Then how many solar systems are there in our galaxy? How many planets are there in each solar system? And then of these observed planets, how many unobserved planets do we expect to find? Because our telescopes are not good enough to see all the planets at once, so we are automatically underestimating them. And this is a bit the same for our materials. And of course, finally, we have a fraction of these planets which might have life. For materials, we are trying to find useful materials. So first we see how many times our quaternary Zintal space fits in our total material space, how many of these materials families we have in our Zintal space, how many materials there are in each of these families, and then how many more there are for each one that has already been experimentally found. And then a fraction of this will be useful. All right, so let us now try to estimate these different numbers. So what we do is we take 3 of these families and then we look at them a bit closer. So what does these materials look like? This is the first one. So we have a box filled with atoms, and this box gets kind of repeated in all directions. So you get these kind of layers of these big atoms spaced with these other layers of these kind of, they're kind of chains that are formed. And then we have a second material, which if you've ever seen the crystal of structure of salt, is a bit similar, except that there here are some kind of tetrahedrons or molecules which have been stacked inside. And then finally, we have our third family, which has this kind of weird, let's say, a spiral kind of shape inside. So these are all already kind of complicated crystal structures. Now, for the first one, 6 are known. The second one, only 1 was known. And for the final one, only 4 materials were known. And so what we do is we create a database of hypothetical materials by effectively substituting similar atoms within these crystals. So if we have this cesium atom, which was a blue atom, we substituted with these 8 atoms from the same part of the periodic table, and then we do the same here for lead, for instance, from this blue part, and for selenium from this yellow part. And then you get 3,000 options for the first family, 2,000 for the second, and 1,700 for the third. So now you want to kind of figure out how many of these are stable. And for this, we will use these quantum mechanical simulations. So how does this typically work? We take this candidate material and we push it through a simulation software here called VASP, which runs this quantum mechanics and finally gives us the energy of formation. So which tells us whether it is stable or not. Let me walk you through this. So here's, for instance, this crystal structure of cesium, lead, phosphor, selenide. We replace the atoms, but because we replace the atoms, which have different sizes, let's say, so pretend they are balls of different sizes. Now the geometry is a bit wrong. So first we have to adapt the volume. Then we also have to let all these atoms move around a bit within the cell. And then this box will actually also change shape, which is quite complicated. And then finally, we actually manually, again, compress and expand this material a little bit, both to examine how soft it is and to make sure that we really have the right crystal structure. So I say how soft it is. Why? Because so if you start with this material here at its, let's say, original volume, if you push on it and the volume becomes smaller, the energy will go up. And if it goes up a lot, it means that the atoms are repelling each other very much. And it means it's resisting the pressure you're putting on it, and that it's actually not very soft. And the same, of course, if you're trying to pull the material apart. So from this, you can kind of estimate the hardness without bumping your toe, let's say. All right, so we use this to get like a final volume, and then we calculate this formation energy. And if it is smaller than 0, meaning you gain energy when you create this material, then we say it is stable. If it's positive, meaning it costs energy to make this material, then we say it is unstable. Okay, we normally take like a safety margin, but that's not that important right now. So we get again our materials here. And if we do these calculations, which are quite a lot of calculations, so about 20 per material, so that's like 60,000 calculations, we see that we get about 108 stable materials, which is much more than the around 6, I think, there were originally, which is about 1 in 30 here. For this material, we found another 100, which is about 1 in 20. And for this material, we found another 100, which was here 1 in 8. The reason that we are finding more materials in these families is actually because we did not simulate everything. We started using artificial intelligence, which allowed us to find the materials much faster. But I will get back to that very soon. First of all, let's see, now we have some numbers for how many stable materials there are, if we can fill in this Drake equation. So what do we need first? We need the number of materials in material space divided by these quaternary interfaces. So how many times our space fits in the space of all materials. If we imagine that we have found as many materials or the same fraction of materials in our space here compared to that of all materials, then around 1 in 100 of the found materials are these interfaces. So there are about 100 times more materials. Then we need to see how many families there are, and these are also about 100. There are the 25 real families which have multiple crystals, and then 75 which are completely unique. But given how many new families or new crystals we just found in these small families, they're probably just unexplored. So this is again a factor of 100. Finally, the observed materials per cluster are about 1, and the number of unobserved ones, so the number of materials we find within each cluster, is again about 100. So this means that if we say the useful ones, or all of them, the ones that are stable, that there should still be about 1 million of these materials in this space, while only about 500 or in this total material space, of which 50,000 are known and only 500 are added each year. And this is just for quaternary materials. So there are many, many more materials left to find. And this is, of course, important because if this was not the case, then we would have to actually modify existing materials by, for instance, adding small impurities of other elements. All right. So there is plenty left to find. And now we will have a look at what artificial intelligence is, so that we can see if we can find them a bit faster. Because while these quantum mechanical simulations have sped up over the years, they're still not fast enough to really create millions and millions of these materials. So what is artificial intelligence? Artificial intelligence is actually kind of a way that you use computers to extract information from data. Now, what is different from the classical way is that you really rely on your computer to do a lot of this automatically from incredibly large and complicated data sets. So let us start a bit simpler first. So the simplest AI type of method that you see is actually linear regression, which most of you have used before. So you have some data points, you draw a line to it, and this line in this case has the meaning that if the percentage of some element that you add to, for instance, a metal goes up, the metal becomes harder. Now, making this kind of line is very simple and it's very easy to interpret. So this is more statistics, but it's not guaranteed that it's a line. It could be this kind of complicated relation, meaning that you need to add a certain amount of this element before it starts having any effect. And there are actually like an infinite amount of curly curves you could fit through this. So if it is complicated like this, you'll have to add a lot more data points to get an idea about it. Now, what makes you go from here to like real artificial intelligence? That's mainly the complexity of the data. So here we just have the percentage of the element, but all kinds of things could play a role. It could be the temperature at which it's produced, how long it's been at that temperature, whether you dip it in water, but you could add all kinds of weird variables, maybe all kinds of weather type of things and so on. Even the person who is making the material could have an effect. And you can combine all these kinds of weird type of inputs in an artificial intelligence algorithm, and it will try to get the output that you want. In this case, the hardness, but it could, for instance, also be like 10 materials properties. And the beauty of artificial intelligence is that you can extract this all automatically, provided that you have enough data. All right. But if you do not have a lot of data, then you should honestly stick to these kind of simple models. So one thing you'll make a lot of use of is what is called active learning. And that is that you're actually using your machine learning while you are producing your data. So in our case, you want to predict material properties, and you need to like somehow tell your machine learning, your artificial intelligence, just yeah, what these materials are. Okay, we look at these boxes with atoms and we interpret this visually. But the artificial intelligence actually expects everything to come in kind of numbers. So in this case, because we are looking at crystals, which always have this same crystal structure, we can just give it some information about the atoms. How easy is it to make bonds with this atom? How is it built? An atom is made up of a core and a number of electrons. How easy it is to add an electron, how easy it is to remove it, and things like that. And with these simple properties, you can actually build very good prediction models, provided you then show it the data. You feed this data into the model, and then it kind of learns the chemistry, which is very specific for that crystal. And then you can get, for instance, the formation energy. Now, what makes or what's the difference between normal learning and active learning is that, for instance, you take 30 materials, you train a model, and then you look at how this model predicts the other materials in your space, and you ask it which one might be the most interesting to try next, to simulate next, or to make experimentally, which is of course more accurate but much more expensive. And the models that we use to make this kind of active learning approach are called Gaussian processes. So what a Gaussian process does is make a prediction for your property, for instance, the hardness, but it actually does not give just a number, but this kind of bell curve. So you have most likely seen that at some point in your life as a form of statistics. So it mainly means that there is most likely this property, let's say 50% or something, and then part of your model can have, or there is a certain chance that there might actually be a slightly different property. This gives you kind of a measure of uncertainty depending on how wide this bell curve is. So with Gaussian processes, you can perform this kind of regression model. So this looks like this if you are trying to predict this curve, for instance. So what you see here is that, for instance, here the model is very certain. But if you're trying to find the minimal value, for instance, the minimal hardness, then you might say that this area, even despite it being so uncertain still, is actually not that interesting, because even given the uncertainty, you'll never get as low as this point. But if we look here, for instance, the uncertainty is so large that the point might even still be lower. So you can use this to kind of abandon parts of your material space before you've even properly explored it. And the key is a bit to choose how much you want to explore your space versus how much you really want to go for what you're looking for. In our case, stable materials. All right. So let me give you another example of this. So here we kind of want to look at defects in silicon. So these gray atoms here are what silicon looks like. This is the same as diamond. And you can actually add other atoms in here which create defects, which are sometimes useful, for instance, to make a transistor like occurs in your phone. Here we have kind of three types of defect. One where you just push an atom in between the other atoms, one where you actually replace an atom, and one where you take two atoms out and then put another atom in, which is mainly interesting if you have a very big atom, let's say, else your crystal will get pushed apart. If you look at these different defects, so if you put 72 different elements on these 6 possible positions, you get quite a lot of combinations. So it is actually for 2 materials using 2 methods, and that were about 1700 calculations. Now, if you look at the results you get for this, look for instance at the red curve, which is how much energy it costs to replace an atom in silicon with these other atoms that you see here on this axis here. You see that the curve is actually quite boring and smooth. So all of these are pretty much flat. And in this region here, you see that it's almost a straight line. So it's not really a straight line, but if you would say we just simulate like 2 points here and you pull a line through it, your errors aren't going to be that big. So that kind of shows you already that with simple machine learning, you can probably kind of predict what this will look like even from a few points. And so we try this for a bit of a more complex situation where we actually replace two atoms. Note, of course, first of all, so if these atoms are in these specific positions, you already have around 2,600 combinations, which gets a lot worse still if you would, for instance, replace different atoms within the box, as then you could have many different types of combinations still. But we are going to stick to the ones which are in these positions and try to find the ones with the lowest energy using this kind of active learning. What's also important to realize again is that we repeat these boxes. So in actuality, these two atoms are actually next to each other, which of course allows them to interact in very specific ways. All right, so we saw this already, and these are the results you get from that. So what do you see here on the axis are just all the atoms going from the lightest ones, hydrogen, to radon, and here the same. You get this kind of periodic structure because we are going through the periodic table. So each of these blocks is a new row of the periodic table. We are looking for the lowest energy combinations, which are these blue regions. They're kind of valleys, whereas the red regions are the most unfavorable ones. The most red regions are things like noble gases, which don't really like to bond with anything, or atoms which are just incredibly big and completely destroy your crystal. The lowest energy ones are, of course, things like silicon itself and the elements which are very similar to it, so which are very near in the periodic table. And you really see this behavior reoccurring as you go through the periodic table. So this means that you are going down in a column of the periodic table and seeing the same behavior. And this is very interesting, that this kind of smooth and clean behavior, because we create this surface with only about 10% of the data. So this actually shows that the model makes quite good predictions. But while you see that most of this region here is quite pretty, there are also regions which are very messy. And these are regions which our artificial intelligence actually decided that it was no longer interesting to explore them. So the model does quite bad there. And we can actually look at how confident the model is in making these kind of predictions by looking here. So you see that the most interesting regions on the left, so the lowest energy blue, are also the regions where it is most certain. So these are also again blue here. So it actually is quite certain about these entire valleys here, with the most certain regions being these really deep double crossing valleys, let's say. So this means that these models work very well and that you can save up to 90% of your computing time. So that is very interesting. Now, we have some problems here still. So what we did so far was use artificial intelligence to speed up the discovery of similar materials to this kind of example materials. So we always kept the same crystal structure, which means our model kind of learned the chemistry very specific to that crystal structure. But of course, in reality, there are all these different types of crystal structures, and we have to kind of start over each time we start a new crystal structure, even though the bonds that kind of occur in these crystals might be very similar. And it would be much more efficient if we could kind of recycle this information, if we could learn from what we've simulated already. But for this, we would have to teach an artificial intelligence to understand what these crystal structures look like in 3D, and that is kind of complicated. All right, there is actually another problem, and that is related to that one, being that all the simulations we did so far are kind of static. They are at absolute zero, where the atoms are not moving around. But if you are at real temperatures, your atoms do move around. Here's, for instance, a hydrogen on a silicon surface, and you see that it bumps around, and sometimes it will actually try to dig itself into the surface, and that means that its energy is actually changing. So if you would just look at the composition of this, which is just silicon and hydrogen, our machine learning models would not be able to see the difference. So we really have to show it what specific geometry this crystal is at, or in this case, exactly where this hydrogen atom is at the time. So we have to go to something more complex, and that is deep learning. So deep learning is the method that you typically hear about in the news when they talk about artificial intelligence, because it is just so popular. And why is it so popular? Is because it kind of learns how to make this kind of input features directly from raw data. So before we chose certain numbers which we thought were a good way of representing our atoms, like how heavy they were, how many electrons they had, and so on. But there are many of these, too many to put in most machine learning models. And there are actually, if you have enough data, methods like deep learning which can decide for themselves not just which ones are interesting, but how to combine them to form even better kind of inputs to process to predict material properties. Let me explain it a bit further here for images, which is one of the most popular applications of deep learning, because they are so complex. So an image is kind of like a square of pixels, and each pixel here, for instance, might be a 0 if you look at it as a number when it's black, and 1 if it's white, and like 0.5 if it's gray, for instance. And somehow this model is going to have to kind of make combinations of all these pixels to predict shapes, and finally predict what you want it to. For instance, is it a cat or a dog in a picture, or a man or a woman, or something like that. So what does it do? It takes all these pixels and it gets it in a first input layer, and it starts kind of making all kinds of random combinations, of which it will learn which are the best ones by looking at a lot of data. And then by making these kind of combinations of pixels, it can kind of detect what edges might occur in the image. So it might say that there are edges under this angle or under that angle, and we call this kind of filters. So at the first layer, you might have a new set of numbers for which the first one might mean that that edge was detected, the second that edge was detected, and so on. And then you can continue. You have all this information on what edges are detected, and we use this to build shapes, to build noses and eyes and so on, and see which ones were detected. And if you know which of these simple shapes were detected, you can start building more complex shapes, like faces, for instance. Now, in an image deep learning model, you're actually kind of using a square kind of filter that you kind of pull over your image to detect these kind of shapes, which we call a convolution. You can actually, what people do is train these kind of deep learning models on very large image databases to predict what kind of object is in there. But since these edge detectors are very generic, you can then actually use part of your model for any kind of other application, for instance, to classify cats and dogs and so on, by just then adapting the parameters of these final layers, which makes it much easier to make good models with small data sets. All right, so now we kind of want to do the same thing with crystals. But crystals are, of course, not images, and they are a bit more complex since they are 3D structures. So what we do is kind of look at the environment of our atoms. So for each atom, we start in the same way we did before. We have a certain amount of numbers that describe the atom if it was completely alone. So how many electrons it has, how heavy it is, and so on. Then we have this for all these different atoms. And we just look at which ones are, for instance, the nearest neighbors of this specific atom. And then we ask the neural network Okay, combine all these representations of these atoms in a way that is most useful to predict our property. And so it builds this kind of function that transforms all these different types of atomic descriptions to something that describes not only the central atom, but also its environment. And it does this for all the atoms in our crystal. Now, this is what happens in one layer. But after the first layer, you then have a representation of each atom with its nearest neighbors. And if you then allow it to mix again these representations, you will also get information on its second neighbors. So you kind of are able to build more complex materials or collect more complex information on very large crystals, the deeper your model is. And that is again the power of this deep learning, where in the image case, you're able to build more complex shapes. And here we are able to study more complex environments. Finally, you kind of condense all this information into one big representation of the entire crystal. So you just throw all numbers together, let's say, and then you do the task you want to do, be it determine a material property or say if it's a metal or not, which is kind of the equivalent of saying if it's a cat or a dog or not. But the function that you have within this kind of deep learning model is actually mathematically, writable in theory, but since it has like 1 million to 100 million numbers in there, it is very unpleasant to write it out. So it makes sense, but you'll never be able to have like this kind of clean formulas you have in standard physics. All right, so as I said, we combine these to get, for instance, the energy. One application for this that we've tried was done by a master's student, Jasper de Witte. And what he did was train this kind of deep learning model on a very large database of thermoelectric properties, so of very diverse materials. This database said, how good are these materials? And then we were able to actually make a model that was that could evaluate how good a material was as a thermoelectric in a matter of minutes. So we just evaluate the entire database I showed before, which took like years to create, using this model, and ranked them as possible thermoelectric candidates. And there are actually many ways to do this. For instance, Fleur, who we saw before, try to get similar descriptions and similar predictions, but by getting this information on the atoms from literature. So by looking at which elements are mentioned together and so on. So this is sounds completely different, but in the end, the models that you use are quite similar. You just have to pre-process your data in a way that it becomes numbers that the models can read, be it replacing text with numbers or replacing these atomic environments with numbers. All right. Some other applications that we've tried, I'll show here in the form of videos. So here you have this very large cube of silicon where atoms have been removed. And if we then just put it at high temperature and we watch it evolve, something which is completely impossible at a quantum mechanical level without artificial intelligence, you can actually, let's see if this thing can handle it. We can see how these missing atoms move around to form this giant missing blob, let's say. So here you see this giant hole forming, which is actually like 1,000 atoms big. And even if you just had 1,000 atoms, it would take around 500 computers to just do one of these time steps. And this might be thousands or hundreds of thousands of time steps to see this kind of evolution. So this is quite amazing. I also want to show some applications by other people. So let's see if we can get this, my browser here showing. So the quality here is not perfect, but once I run the video for a bit, you will see what happens. So this is again a giant box with around 4,000 atoms in there, I think, and they are carbon. They are all spread out. But if you then put them again at very high temperature and you wait a long time, you see that things start forming. And these are actually these kind of nanosheets or carbon nanotubes and buckyballs and things like that that you might have seen before. Also, yeah, these are basically graphene sheets, and they all form spontaneously. And this is extremely interesting because this model has actually never seen these things before. It just learned some chemistry from actually seeing very small molecules and a bit of extra examples of how these carbon bonds break. So this actually means that it can really learn chemistry from these very small local environments. Here is another small example. And that is of a protein which is surrounded by water, which is these kind of red things. Well, let's try again. Or these red things here, and also some vitamin B that is not really visible here. But effectively, this protein is something you would see in egg white. And of course, it is very useful for biological applications if we can see the interaction between proteins and medicines, for instance. But these are usually way too big to solve properly using quantum mechanics. And here again, a model was used that that was trained only on small molecules, and it is able to maintain this shape and even see some dynamics of this very complex system. So this was work by Alexander Isaev, who is working mainly on this kind of drug discovery type of applications. All right, so let's see where we are at. So here you also, let me put this thing back. So here you see a bit more these sheets and kind of forming buckyballs a bit zoomed in, which in the end look like this. Okay, so as you can see, you can actually do quite a lot with these models already. We are really going to larger scales of systems, meaning we'll eventually get really into the biological area of tissues, of viruses, and so on. But one thing that we are missing still for our materials discovery application is to find new crystals. And this is something people are working on now, which I am showing here on my last slide. So what you can consider our current models doing is that we take a crystal and we kind of compress it into this smaller amount of numbers, which is like a simplified way of maintaining the most important information of our crystal for our properties. So before that was if certain types of noses or eyes were detected, and in our case it will be whether certain types of chemical environments exist in this crystal. Now if you make this space very small, you can actually visualize it, and you might see something like this, that all the stable materials are together and the unstable ones are together. And then if you could make a model which goes back from this reduced kind of representation to the actual crystal, since you know which crystal belongs to each point, then you could actually also look at points which you have not simulated yourself, which should be new crystals. And so this kind of work is actually starting to work, and this is quite interesting because you can end up making models which do not just simulate existing materials, let's say, but they can actually just show you entirely new crystal structures, and probably thousands per second. So this could really be a way that we can explore the entirety of material space in a matter of days, let's say. But of course, it is extremely difficult to make a model which works on a very wide range of materials. All right. So this brings you a bit to the end of my presentation. So what should you remember? Of course, Quark did not invent fire, but the things we learned from Josephine were, of course, very important. We saw that you do not need to actually get the exact properties of materials, but rather you just need to be able to compare them. You need to be able to build these material spaces that you can kind of mentally explore. And then you can really try to optimize what you need for your application. And you can also take things into account, like how expensive, for instance, certain elements are, how rare they are. And these are all very important in your journey to find a new material. There are a lot of materials left to discover, and we can actually simulate these properties, but they are still very slow. So we should use this kind of active learning and artificial intelligence to speed this up. And maybe, just maybe soon, we will be able to really discover many, many new materials if we can get these very fancy models to work. Okay, and so with this, I'm going to end. I'm just going to show you a minor advertisement slides still. So if you're interested in this kind of research, we have all kinds of master theses going on if you're a student. And there is a kind of an explanation moment tomorrow at Thursday at 5 p.m., which you can visit in Gather Town here. And there's also information on our thesis subjects on the website. We also have this PhD position open, which we will hire someone for very soon. But if you're interested in this kind of AI thing and want to help build the next generation of nuclear reactors, send us an email as soon as possible. And finally, we are also developing this kind of course for the materials industry, which can be interesting for just about anyone. And if you want to help test it, I would say have a look at the website and send us an email. Then we will get further in touch with you as new material is developed. So now I would say if you have any questions, feel free to ask them. Silence so far.
They're all typing right now, probably.
Mm-hmm. After the presentation, there will also be a kind of a virtual reception in Gather Town, which Fleur will introduce in a few minutes once the questions are done. All right, I see the first question. So when we don't use AI for simulating, quantum computers seem to make simulations easier. Yes, there are actually ways that quantum computers, first of all, speed up quantum chemistry, of course, because they can simulate quantum behavior. But indeed, for machine learning, there are also ways that you can use quantum computers to speed up machine learning, though they're still a bit in their early stages. The way this works is mainly by being able to traverse these simplified spaces that we saw in the last slide. In a more efficient manner. So you can kind of have this more complex description of this space using your quantum behavior and then optimize more efficiently in there. But these technologies are still developing. Any other questions or any additional questions related to this one? None so far. Though I hear some interesting clicking still, but...
That's mine, Michael.
False hope.
Maybe while we're waiting, I can already post the link for the Gather Town. Just right after the meeting, we've opened the Gather Town space. So if you feel like joining, having a little talk, grab a beer and come join us. Just in a formal talk. Normally would have one in real life, of course, but Gather Town is a nice alternative. You can even play games there, so it's very fun. So come join us if you want to later. The link I have posted it just now in the chat.
Yeah, I guess that is probably about it for the questions then. So maybe we should slowly start exploring Gather Town here.
I think so. Maybe a
All
couple
right,
of
yeah.
seconds, last calls for questions. Michael, will you also be at the Gather Town?
I will indeed participate for a little bit.
Okay. So if there are any questions, you can find them here. I would also join. So if you like to, come join us in the Gather Town. With this, I think we can wrap
Yeah.
this lecture, I guess.
Thanks everyone for listening, and maybe see you soon in Gather Town. Have a good evening.
Bye-bye. Thanks for attending.